example before us, understanding the causality and the grammar, pictorial grammar for each element. We have source of effort, which is represented by the symbol SE, and it is connected through a power bond to the subsystem to which it has to transfer power. Now, the characteristic of a source is that it will impose an effort, irrespective of whatever is the flow that it experiences. So, it will impose an effort from its side towards the other system to which it is connected. So this becomes the output of the source of effort. And what is the input to it? Input is flow, but the source doesn't really worry. It doesn't really bother whether whatever is the flow, it doesn't bother about it. It will continue to impose the effort, irrespective of whatever is the flow that it experiences. This is the characteristic of a source of effort. Now, you must have seen as an example in the mechanical, in the electrical engineering domain, we have a power supply. Let's say if we consider the 230 volts AC power supply. So we know that the effort, the voltage is imposed by the supply, and we may connect some reasonable load to it, but within reasonable limits, you will find that it will draw the amount of current, the load will draw the amount of current that it is needed, but it will not be able to load the source or create a drop in its potential. So this is the characteristic of a source. In the mechanical engineering domain, we have a wonderful example of the force of gravity. We have any mass which is near the surface of the earth experiences a force. That force we call as the gravitational force. We write it as mass multiplied by the acceleration due to gravity. Now, this is a constant force near the surface of the earth corresponding to that mass. Now, irrespective of whatever is the motion of the mass near to the surface of the earth, the force that acts on it remains the same. So it is as if the force is being imposed on the mass, irrespective of whatever is its or flow. So that's an example of a source of effort. Naturally, as discussed in our previous lecture, the idea of causality says that the end, the subsystem which receives the effort, now you can see the effort arrow, it's going like this, and so this end will receive the stroke. The end which receives the effort receives the stroke. This is the causal stroke. Automatically, the other end, that is the source of effort, it receives flow. We have the source of flow. In a similar manner, we have a source of flow. It is represented by the symbol SF. Here also, it provides power to the subsystem to which it is connected. But what it does is it imposes a flow. It imposes a flow in any energy domain. It could be current, it could be velocity, in any, it could be volume flow rate. So it depends upon which energy domain it is in. So it imposes a flow on the subsystem to which it is connected, irrespective of whatever is the effort that it experiences. So here also the output of this source is actually the flow, which is it's the source of flow, and whatever is uh, whatever is the effort that is decided by this subsystem is received by it, but it has no effect on the flow that it produces. The flow is decided by the source of. We have an example in the electrical domain itself. We have current sources in electrical systems. So those current sources are capable of providing currents, whatever designated currents they are supposed to produce, irrespective of whatever is the potential difference across them. This is, of course, within reasonable limits of power. Likewise, in mechanical systems, we have instances of the cam motion. Okay, you have a cam with a geometry, and as it turns, the follower just follows it, follows the profile of the cam. So the motion is imposed by the cam on the follower, but it's the follower that will decide what should be the force that should act on the cam. But you see, usually for strong cams, cams which are driven strongly, the cam does not bother about whatever is the effort or the load that it experiences. It goes on imposing a motion. It follows a particular timing and it just imposes that motion on the subsystem to which it is connected. So these are our two sources, a source of effort and a source of flow. Then we have, of course, coming to the causality. Naturally, the end which receives the effort receives a causal stroke. So since effort comes like this, the causal stroke is placed here. We have junctions also in bond graph. We have two junctions. We have a one junction given by 1F, and so we have these one junctions. A one junction is usually represented like this. The subscript F over here is indicative of flow, which is represented by this one junction. All the bonds that are connected to this have the same flow in them. So the flow is common to all of them. Representatively, we have just shown 4 bonds. It does not create power, it does not destroy power. So whatever power is brought into it is immediately sent out to the other bonds. All these bonds have the same flow, common flow. So the question comes now, if there are more than one bonds which would bring in flow into this one junction, will the grammar of this one junction be valid or not? See, this one junction is supposed to maintain the same flow in all the bonds connected to it. If 2 bonds bring in the information of flow into this one junction, naturally those two flows could be different, and in that case the characteristic of this one junction would be lost. The nature of this one junction would be lost, because then it will not be able to ensure that all the bonds have the same flow. So the rule for a one junction is that only one bond should bring in the information of flow into it. All the other bonds should accept that flow. So here we have the efforts like this, but here we have shown a bond which is bringing in the information of flow. You can look at the causal stroke. getting this information of flow, and they are the causal stroke comes here for them. So only one bond brings in the information of flow into this junction. This is going to be one junction representing a flow, and we can have any number of bonds connected to it. Let's say that we have a bond like this. We have another bond we have third bond like this. Say a fourth bond like this. Sorry. So we have these bonds. We have shown four. We could take one more just to differ from what was shown earlier. So let's say we have five, and let us bring in power just to make things clear. So here we have two bonds bringing in power and three bonds taking out power from here. And because it's a one junction, all the bonds have the same flow, F. Okay. And the efforts could be different. Let's say this is effort 1, effort 2, effort 3, effort 4, effort 5. Now, we know that power that is coming in, that is P1, another bond is also bringing in power. So we have plus P4. Okay, this is the power associated with this bond, and this is the power associated with this bond here. And these are, this is the power that is coming into the one junction. The power that is leaving the junction is P2 plus P3 plus P5. Okay. Now, if you write this in terms of efforts and flows, you can write P1 as E1 into F1, but F1 is the same as F. Similarly, E4 into F. And this is equal to E2 into F plus E3 into F plus E5 into F. And you can see on both these sides, F can be taken common. And so you get the result that effort 1 plus effort 4 is equal to effort 3 plus effort 2, effort 2 plus effort 3 plus effort 5. Okay, this is what was being explained in the slide, in the PowerPoint slide. As a result, we get effort 1 is equal to effort 2 plus effort 3 plus effort 4. Okay, is a common flow junction, but it can also be used as an effort summing junction. In the same way, you can have a zero junction here. You can have these bonds, and this suffix E here represents that all the bonds that are connected to this junction have the same effort. So we say that now suppose if more than one bond brings in the information of effort into the zero junction, okay, then what would happen? It's a zero junction. It is supposed to be a common effort junction. Common effort junction. So naturally, all the bonds that are connected to it should have the same effort. This is possible only if one bond, any of these bonds, but only one of them should be bringing in the information of effort into the junction. If more than one bond brings in this information, then there will be a clash. Okay, so in that case, the grammar of the zero junction will get violated. It will not be able to maintain its characteristic, and so it will. It's necessary that the grammar dictates that only one should bring the information of effort in the zero junction. So let us say that it is this bond which is bringing in information of effort. All the other bonds have to accept it. So all the other bonds have to accept it, and all the bonds have the same information of effort. Be different because our transaction has to take place. Just like the one junction, the zero junction does not store power, not destroy power. It does not accumulate or destroy power. It just transmits power. It just whatever it receives, it just sends out. Net amount being zero. So here also you can obtain a similar relation. In this case, F1 is equal to F2 plus F3 plus F4, and you can see it can be said that the zero junction is a common effort junction or a flow summing junction. Okay. So before that, this was about the one junction. I had made an explanation, but somehow I think the presentation was not going on. But you already have the audio with you, and this is about the zero junction. Okay, so we are now going to proceed further. We'll go to the causality of the I element. For the I element, it's very important because it deals with momentum, and it's associated with kinetic energy. So you have the mass in this particular example. You have a mass in the mechanical domain, and let's assume that this mass is moving with a velocity v. The mass is m, and the velocity with which it moves is v. Now, let's say that we have this bond to which this I element is connected, and this I element represents inertia, and the parameter associated with the I element is the mass or the parameter, mass parameter or inertia parameter. Now, there has to be an effort and a flow. For the I element, the effort is equal to the rate of change of the generalized momentum associated with this I element. And the flow is a function of this generalized momentum. Okay. Now, what does the I element do? If it is provided with effort, that means in this case, if you're applying a force, it becomes an input to the I element. It becomes a cause for the I element. The I element decides the I mean, in fact, it contributes the state P or momentum. It's called generalized momentum. Because it's associated with mass here, it's we call it as mass momentum or just the momentum. And uh, what it does is it integrates this input which is provided to it, and it determines the momentum. And then it produces an output which is a function of that momentum. So this is the simple role that the I element plays. It receives a cause as effort, it integrates the effort, produces momentum, and it produces an output which is a function of the momentum. Now, in the case of Newtonian mechanics, it's a simple linear relationship between the flow and the momentum. So it's just that flow is equal to momentum divided by mass. So it's just a straight linear relationship. Okay. Uh, so this is the output which is produced by this I element. If you look at this part here, you will see that the output, we go from the output and trace it back to the input. So the output is the flow, and that is a function of the momentum. It is a linear function in this case. It's P by M, and that's equal to 1 by M integral P dot d tau. Okay, and the integral is from Ti to T, where tau is going from Ti to T. Tau is a dummy time variable which we have taken, and it goes from a past time up to the present time, and that is equal to 1 upon M integral effort, this integral. Okay, so what it is doing, what this I element is doing, it is taking the cause and integrating the cause, okay, and then creating a function and then producing the output. So for the I element, you can see that because this is the end which receives the effort, the causal stroke will come here. Okay. So when the causal stroke comes here, relationship is valid, and we say that the element is in integral causality. It can also be said to be like this, that the effect is a function of the integral of cause with respect to time. So this is a characteristic in general for the I element. In fact, this is a general statement that the effect depends upon the history of the cause, and it keeps a track of the cause. So you have this integral from an initial time to the present time. And the characteristic of an integral is that it just accumulates, okay, with the correct sign, of course, it just goes on accumulating. So it keeps a track of the history of cause. So this is very important in terms of the discussion, because you know that the present effect is due to a function of the integral of the cause. So it is an accumulation of the cause that was taken into consideration right up to the present time, from the past up to the present time. So that is effect. And you can also write this as the derivative of the effect with respect to time is a function of the cause. So this is a general statement, and this is how we can write it. This form of causality, where the causal stroke is placed near the I element, is called is natural for the I element, or it's called as integral causality for the I element. Okay. Now, coming to this integral causality, Let us move to the discussion part. I'll explain this. The I element. You can see that the power is directed towards the I element. And let's say if it is a mechanical domain, the mechanical domain, uh, its inertia is mass, or in the rotational domain, it is moment of inertia. But let's consider the mass as we have taken. So here we have the effort that is being applied here at the time t as equal to the rate of change of the momentum. So this effort, we know from Newton's laws that it results in the change in the momentum of this mass. So the I element just integrates this. It integrates and determines this momentum. Okay, and so this becomes the state associated with the I element. So the information of effort goes in like this. Okay, and the I element produces an output. It produces an output like this, which is flow. So this flow is actually equal to the momentum at the time t divided by the mass in this case. But in general, it is actually just a function of the momentum. Okay. In the electrical domain, we take this momentum as it's on account of inductance, and whatever potential that you apply across this inductance results uh, in the change in the flux linkage, which you call as rate of change of the electrical momentum. And electrical momentum in this case becomes the flux linkage. Okay, so in mechanical domain we have linear momentum or angular momentum. In the electrical domain we have the flux linkage, and it produces an output which is a function of that momentum, of that generalized momentum. So in this case it is linear. Now if we see, if we analyze the relationship between, I think we have I have a couple of minutes. I'll just explain to you quickly. If we look at this relationship between the effort and the flow and the momentum in this case. So here we have the flow and the momentum rather. So here we have, let's say, so let's take momentum here, and let's take flow here. Okay, and we know that the relationship is a linear relationship in Newtonian mechanics. So we could take this relationship as just a simple linear relationship in Newtonian mechanics. So at any time, the momentum at any time here it's given by this flow so this momentum here results in this flow, and this flow is a function of the momentum. Okay, and in this case the relationship is linear. So if we see the energy that is produced on this account, you can write in this bond, you can write this power as power at the time t as equal to effort at the time t multiplied by the flow at the time t. Now, effort is actually rate of change of, let's write it in terms of tau, the momentum, and we will keep flow as it is, and here we'll have this integral with respect to time. So if we integrate, or rather right now I'll just keep it as it is. So say this is now this becomes p at tau. So suppose if you integrate this, you will get energy. So p integrated with respect to time from past time, let's say from an initial time to the present time t, this will be equal to the integral ti to t. This is dp by d tau into f. Okay, so we can also write this as integral of f dp. But now, because the variable has changed, the variable of integration has changed, this will be momentum at time ti, and this will be the momentum at the time t. Okay, so if we integrate this, you can see that we can write it. In fact, if we consider this particular example, we know that flow is equal to momentum upon mass. So we could write this as integral momentum divided by mass. This is flow dp, and momentum is going from pti to pt, and this will become equal to p square by 2m, and you can set the limits. So this is integral from pti to p at t, and when you substitute, you will get here 1 by 2m into p at t square of this minus p square ti. Okay, now this is if you are to write it in terms of mass into velocity, you'll get m square v square minus m square v square here. But this is at a particular initial momentum at a time, so it's a constant actually. This would be some kind of datum momentum, and this is whatever is the present momentum. So momentum square. So in that case, you could also write this as equal to 1 by 2. 1 m would go. So you could write this as mass multiplied by, I'm sorry. Yes, 1 mass would remain. We can take it out common. So we'll take this out as common. Mass multiplied by, so here you would have velocity at the time t, which is corresponding to the flow variable here at the time t, square of that, minus the velocity at the initial time ti, that is corresponding to flow at the initial time. So you can see it corresponds to the change in the kinetic energy. Okay, so the change in the kinetic energy. So this is change in kinetic energy, and this is what it is represented by. So the I element is associated with kinetic energy. Momentum is associated with kinetic energy. I hope everything is clear to you so far in our discussion today.